We said last week that after IBP reduction, master integrals satisfy differential equations, and they all generically come out to be of this form. So I is a vector of master integrals, and A is a matrix that, if it comes out of IBPs, is rational in your kinematic variables and in epsilon. The vector of master integrals is, of course, well, it's some basis. You could choose a different basis. So you could do rotation. M is a matrix, which may depend on x and epsilon. You then get a differential equation, which is of the same type for J, which is J being the new basis, where the new matrix A prime is related to the original matrix, essentially by a gauge transformation. And conjecturally, there is some algebraic matrix M of x and epsilon, such that you can always bring the matrix into the form where it is linear in epsilon. The epsilon dependence is simple enough that it is linear. And in particular, the simplest case is that A1 is 0, which is something that is often called the canonical form in the literature. And its advantage is clearly that the solution of the system is then simply path-ordered exponential. Well, it's always a path-ordered exponential, but the advantage is that now you see the exponent is proportional to epsilon, so that when you expand the exponent, you can easily truncate the expansion in epsilon. And I of x0 is the initial point. So that is what we said last week. So from that, well, so here, we've seen that the natural objects that come up when you expand the path of the exponential are iterated integrals. And you see here the structure again for the box, where your matrix A tilde, which is before was called A2, is a sum of two terms with two matrices A0, A1, which are constants, and two differential forms which just have poles at x equals 0 and x equals -1. And when you expand the path-ordered exponential, you get at every order in epsilon, you get these iterated integrals. So the solutions to the differential equation, if they are in canonical form, will generically involve iterated integrals. It just comes out of expanding this path-ordered exponential. So that's why in this lecture, we will look a bit more closely at iterated integrals to see what kind of functions you can get out of these kind of differential equations. And so the naive definition of an iterated integral is what we've seen on the previous slide. It is essentially an integral where you start integrating from some base point x0, which is the same for all of them, and you integrate the outermost integral you integrate up to the endpoint. The next integral you only integrate up to t1, where t1 is the previous integration variable, and then you continue like this. So that is, if you want, a naive definition of an iterated integral, right? So you just integrate, you have a nested integration always up to the previous integration variable. Now, sometimes for applications, this language may be a bit too naive, and that's why I think it's useful to go to a slightly more evolved language, which is the language of differential forms. Now, since I'm not sure if everybody is fully up to speed with what the differential form is, I think it's useful to spend at least 2 slides to give some basic review, some very naive and pedestrian review of what the differential form is. If you know what differential forms are, then the next 2 slides are probably very simplistic. So, to understand what differential forms are, take as an example just the real space with coordinates x1 to xn. So it's n-dimensional real space with coordinates x1 to xn. Just to fix the idea. Now, a differential form, you should just think of it as some linear combination of objects, which are, well, they are functions of the coordinates. And then you have these differentials. And a K form is something that has K differentials. And then there are these wedge products. These wedge products are these little guys here. So that is called a wedge, which you should think of just as multiplication. So it's a way to multiply differentials. The only thing you need to know about this wedge product is that it's totally antisymmetric. So whenever you have dx wedge dy, it is actually minus dy wedge dx. Why? That is because swapping x and y is like changing the orientation of the space in which you want to integrate, because the goal will, of course, be to integrate these things that have the x's. And indeed, you should, if you're not familiar with differential forms, you should just think of them as integrands. The K form is nothing but a K-dimensional integrand. That's, differential forms is just a mathematical language to speak about integrands. And integrands are meant to be integrated on objects. So K form is meant to be integrated on a K-dimensional manifold or K-dimensional submanifold of the space you're in. So let's look at an example, because this was very abstract. So the object omega you see here is a two form. Two form because it has two differentials, dx wedge dz, and sorry, dy wedge dz, which is here, and dx wedge dz, which is there. And in front of that, you have functions of the coefficients. And it's a two form on, say, R3, which comes with coordinates x, y, z. So now I want to integrate it over something. So it's something which has two differentials. So I want to integrate it over two-dimensional space. So let's call it two-dimensional space sigma. And let me just choose some kind of region in the hyperplane. So I just take a hyperplane, which is given by these three equations, where u and v vary between 0 and 1. So this gives me some kind of parallelogram. So I want to integrate omega over this parallelogram. So how can I do that? Well, it's actually very easy to do. The basic idea is that I have these objects, these differentials, dx, dy, dz. But so I have three dx, dy, dz, but I want to integrate over two-dimensional space. And the coordinates on my two-dimensional space are u and v. So that is what, those are the coordinates on the plane, on the parallelogram. So I just use the chain rule to write dx, dy, dz in terms of the u and dv. And what is dx over du? Well, if you go back, well, we had x equals u here. So dx over du is just 1. What is dx over dv? Well, x was equal to u, so dx over dv is 0. So dx is just du. And now you go on like this, and you get what is dx, dy, dz as a linear combination of du and dv. And so then you just plug that in to omega. So omega, when seen as something that lives on this parallelogram that I want to integrate over, well, this was our definition of omega from the previous slide. And so now I just plug in what I know. I know that when I'm on this parallelogram, I know that x is equal to u. Well, you see the colors actually. X is equal to u. Y is equal to v. And I plug in the formulas for the differentials that you have on the just before. And so if you go through the algebra, then you just end up with now something that depends on u and v and the differentials du dv. So that is something they can now naturally integrate over this region uv between 0 and 1. So that's what it was. U and v lie between 0 and 1. So I can easily integrate this guy here over the region uv equals from 0 to 1. That's just a caveat. I need to define my conventions because du wedge dv is antisymmetric. So I have to define my convention whether that integral is 0 or 1. And once that is done, I can easily evaluate the integral of omega over sigma, it just becomes a double integral in u and v, and you just do the integral and you're done. So that was differential forms in a nutshell. It's really just a way to talk about integrants. And if you give you a differential form, a differential k form, and I give you a k-dimensional integration region, if you want, you just use the chain rule to change variables to the coordinates on that integration region, and you do the integral. It's very easy. Okay. So what has this to do with iterated integrals? Well, we can give iterated integrals a bit more of a abstract but geometrical meaning, which will be very useful, as you will see in a second. So for now, let me just, so now I say, okay, instead of just integrating from x0 to x, which were numbers, I live in my space, which depends on all my kinematic variables. So x is now again the vector of all the kinematic variables, for example, s, t, or whatever. And I choose a path, gamma, that goes from x0 to x1. Now, if you take a path, I can always choose the local coordinate on the path. And I choose my coordinate t such that at 0 it is equal to the initial point, at 1 it is equal to the endpoint. So that defines a path. So if I now also take some differential forms, I take n1 forms. Well, I need to take 1 forms because I want to integrate them on a path. A path is a one-dimensional object, so I have to take 1 forms. And I can now just write down what is the integral of my sequence of 1 forms on the path gamma. And if you use this simple rule of just using the chain rule to change variables to the coordinate on the path, you just recover the naive formula that I gave you on the first slide. So at this point, it seems like it is a bit of redundant information to think about these iterated integrals as paths and differential forms. So we will see when we work with them, it's actually very convenient to think about them in that way. We're just choosing a path and integrating the differential forms on this path. But the naive definition is just this iterated integration that we had at the beginning, and you can easily switch from one to the other by just choosing a local coordinate on the path. So these iterated integrals, so what are their basic properties? The first question you can ask is, if you take a path, gamma, which goes from x0 to x1, there's another path which I could consider, which is the path gamma, but going from x1 to x0. I just go in the opposite direction. Now, if it was not an iterated integral, but just a normal integral, so n is equal to 1, then you know what would happen if I integrate in the opposite direction and just change the sign, and just change the orientation on the path. If I have an iterated integral, things are slightly more complicated. I change sign, but the sign is changed sign only if I have well, it depends on the number of iterations that I make. So I get -1 to the n. Indeed, when n is equal to 1, I get -1, so I just change sign. But the other thing that happens is I also need to reverse the order, because now I had ordered my integrations along the paths in a given direction. If I go in the other direction, I have to order everything in the opposite direction. So you can always go back. So you can go along gamma from x0 to x1, or you can go backwards along a path which I call gamma -1, which is traveling gamma in the opposite direction. So that is one natural property of these integrals. The other natural property is that, well, you may have 2 paths, gamma 1 and gamma 2, which, however, share some endpoint. So the endpoint of gamma 2 is equal to the starting point of gamma 1. So I can build a new path, which is just combining the two. So gamma you get a new path gamma, which is just first traveling along gamma 2 and then along gamma 1. And if I have such a composed path, I can decompose my integral, my iterated integral, into iterated sum of iterated integrals on each of the two paths separately, according to this formula. So I have to sum of all possible ways to distribute the differential forms on the two paths, and then I multiply them together and add them up. And if you look carefully, you see that there's a contribution here from k equals 0 and k equals n. Whenever you have an iterated integral without any differential form inside, you just by convention put it to 1. So that's what the endpoints of this summation are. Okay, so that allows you to write an iterated integral where you have a complicated path that's piecewise. If you know how to do the integral on each piece of your path, you can just combine these individual iterated integrals to get the iterated integral on the complicated path. And we'll see an example of that in a bit. This is very useful. The last property, which many of you may know, is the shuffle product. You can actually multiply these iterated integrals. And to get a feeling for that, let's look at the case where I multiply an iterated integral, two iterated integrals of length 1. So I just have one integral to do. And the important thing is that I choose the path to be the same. So I have the same gamma. Okay, so what do I get? Well, let's first introduce coordinates on my path. So I just choose the coordinate t on my path gamma, and I write each of the two iterated integrals in that coordinate. Okay, so that gives me, so this guy gives me this guy gives me that, for example. I just wrote them in coordinates. And so what do it mean? Well, instead of thinking about it as a product of two integrals, I can just write it as an integral over the square with edge length 1. Right, that's the same thing. So I just integrate over the square. I can, of course, split the square into two triangles, shown here in green and in purple. It's the same thing. But if you look carefully, you will see that actually each of these two integrals, the green one and the purple one, are themselves iterated integrals. So if I multiply the iterated integral of omega 1 and the iterated integral of omega 2, what I get back is the iterated integral of omega 1, omega 2, and omega 2, omega 1. So there's some algebra structure going on. Iterated integrals over the same path are closed under multiplication. And the formula is actually very easy. So here, this is the summary of the previous slide. So the integral of omega 1 times the integral of omega 2 is the integral of omega 1, omega 2 plus the integral of omega 2, omega 1. And the way it works is that you should think of it as two stacks of cards. Each stack has one card only. So in one stack, you have a single card, which you call omega 1. So there's one card. These two stacks with one card each. And now you ask yourself, what are the two ways that I could shuffle the two stacks? Well, I can either put omega 1 on top of omega 2 or omega 2 on top of omega 1. And so that is how the multiplication works. And that is also how it generalizes. For example, if you have the integral of omega 1 times the integral of omega 2, omega 3, the way it works is that, well, you have one deck of cards here, which just has one card, omega 1. The other deck has two cards in a certain order. So the order is that omega 2 lies on top of omega 3. And now you ask yourself, how can I shuffle these two decks of cards? Shuffling means that you put one deck into the other, but you're not going to destroy the order inside a given deck. So you're not going to change the order between omega 2 and omega 3. So that means you only have three possibilities. So either you put omega 1 on top, you put it in the middle, or you put it at the bottom. And if you then look at what you got, well, then you see that the integral of omega 1 times the integral of omega 2, omega 3 is the integral of omega 1, omega 2, omega 3 plus the integral of omega 2, omega 1, omega 3 plus the integral of omega 2, omega 3, omega 1. So that's this very simple rule, and it always works with this idea of shuffling cards. If you have two iterated integrals along the same path, you multiply them, you interpret the sequences of differential forms as some decks of cards, and then you have to sum of all possible ways to shuffling these two decks of cards. So such an algebra structure is called a shuffle algebra. And that's always the case when you work with iterated integrals. Okay. Any questions about these basic properties so far? Okay. So then let's look at the fourth property, which is very important, which is path dependence or independence. Depends on how you read it. That's the following. So let's look at the simple example. Let's look at the example where n is equal to 1. So just have a normal integral. So you take a differential form, and you take a path, and you actually take two paths that go from some initial point, x0, to some endpoint, x1. So the initial and the endpoints are fixed, but I choose different paths. And now I can ask, well, if I integrate my differential form omega 1 over each of the two paths, do I get the same thing or not? And I guess you know the answer. In general, you won't get the same thing. But in order to get the same thing, you need the derivative omega 1 to be 0. That just follows from Stokes' theorem, because you see that if the two paths have the same endpoints, then there's a well-defined area in between, which are called D here, whose boundary is precisely gamma 2 minus gamma 1. So my two integrals are equal precisely when the integral of omega 1 over this closed path is 0. But by Stokes' theorem, that is equal to the flux of the derivative of omega through the area. And you can also show that the inverse is also true. Here was actually showed more that if the omega is 0, then the two integrals are the same. You can actually show that the converse also holds, at least with some additional hypotheses. So this is something I guess you know. It's Stokes' theorem, essentially, or it's what you see also in complex analysis. And the integral doesn't depend on the path, if and only if the differential of the differential form is 0. That's just Stokes' theorem. So that is if you have a single differential form. Now the question is, what happens if you have an iterated integral? When you have omega 1, omega 2, omega 3, the sequence of differential forms in there, and you make an iterated integral out of it. So how does this change? It turns out that this idea of the integral being independent of the path, if and only if the differential of the integrand is 0, this idea generalizes to sequences of differential forms, so the iterated integrals. So sequences of differential forms are integrands for iterated integrals. So there's a notion of how you generalize this idea of d omega equals 0. to iterated integrals. We're not going to go through the math because the math get a bit more complicated, but it has to do with a differential form being closed. But now we generalize this idea to sequences of differential forms being closed. The important message I want you to take home is that if your iterated integrals come from a path-ordered exponential, come from a differential equation, then this condition that you don't depend on the path is actually equivalent to the integrability condition that we've seen last week. So if the matrix of your differential equation satisfies the integrability condition, dA equals A wedge A, then your iterated integrals will not depend on the detail of the path, they only will depend on the endpoints. One caveat here, not depending on the path, but only the endpoints, means that you can continuously deform the contour. Obviously, if I put a pole in here, so if I have a pole somewhere in between, so say omega 1, let's say omega 1 is dx over x minus a, where this is the point A, then it would not be the same, but it would be, for example, the integral of omega 1 would be the integral of omega 2, of the integral over gamma 1 would be the integral over gamma 2 plus the residue at the pole. Okay. So this idea that you only depend on the endpoints is a statement that you can deform the contours one into the other without causing any singularities. This is important, okay? If you have a pole in between, then of course you cannot deform one path into the other, and therefore the integrals will not be the same. They will differ by residues. The technical word for all of this property of path independence that you may find sometimes in literature is homotopy invariance. If you don't know what a homotopy is, it's not so important. I just want to mention that if you read some in the paper that iterated integrals are homotopy invariant, it means that you can deform the path in any way you like without causing singularity and without changing the value of the iterated integral. But again, I repeat that if you have a differential equation whose matrix satisfies the integrability condition, that is all automatic. So you don't have to worry about it. But it's good to keep it in mind because it means that you have freedom in how you choose the path. And as you will see, depending on which path you choose, the integral may be more or less complicated. Okay, questions about the iterated integrals? Okay, so then you can ask the question, okay, if these differential equations lead to iterated integrals, I mean, what kind of functions show up in the answer? And in order to get a feeling for that, recall that we said, at least conjecturally, you can find some rotation matrix M whose entries are algebraic functions. So algebraic functions meaning here rational, and they may contain square roots, for example. You can find an algebraic function M such that the differential equation becomes simpler. Namely, now the new matrix of the differential equation has this simple dependence on epsilon. Right? That's what we said. So in order to see what kind of functions come out, the first question you can ask is, well, let's first assume the conjecture is true, and we go to the simpler form of the differential equation, then let's see which kind of functions we could get in that case. And we also said last week that in many interesting cases, actually, A1 is 0. You can make A1 0. And actually, in that case, you even expect a bit more than what I said last week. You actually expect that the matrix A2 that is left over, or the new matrix A prime, it's not just any function of x, but the differential forms that show up in there are logarithmic one forms. They all should take the form of d logs of some functions which are either rational or contain square roots, for example, algebraic functions. So that is the general structure you expect. At least when A1 is 0, you expect that you can bring the matrix A prime into this form where you have some overall epsilon, which is sitting outside, some matrices bi, which are constants. They do not depend on x. And all the x dependence sits in these d logs. The arguments of the d logs are rational functions or contain square roots, for example. Note that this is precisely the form of the differential equation we had for the massless box, where we had these two matrices, A0 and A1, which here would be B0 and B1. And then we had two differential forms, d log x and d log 1 plus x. That's precisely the form we had for the massless box. Okay, so that is, if you want, the simplest class of functions that you can get. So that is the case when you can find a rotation that brings you to canonical form, meaning A1 is 0. And the matrix A2 takes the form of epsilon. Oh, sorry, the matrix A2, the epsilon is outside. So the matrix A2 takes the form of a sum of constant matrices multiplied by d logs of arguments that are rational functions or rational functions in square roots. Okay, so that is the kind of simplest form you can have. So what are the kind of functions you can get? So let's make it even simpler then. So let's say, what is the simplest structure I could have for d alpha I, for these arguments? Well, clearly, if they are rational functions, that is already simpler than a rational function in square root. So let's restrict first to rational functions. If I restrict to rational functions, the simplest thing they could be is that they are linear. Right? So, and here you see, for example, the example of the massless box, which is, well, I said it already in words. Massless box has this form. And indeed, there you see that the arguments are linear. So you have these x, which is linear, 1 plus x, which is also linear. So that is the simplest case of functions that you can get. And that is what we are going to try to understand first, at least very briefly. Before we do that, just a comment, something that you often see in the literature. So you often hear people talk about alphabets and letters in this context. The letters are these d logs, the d log x and d log 1 plus x. This is what people call letters. The set of all letters is called the alphabet. So that's all the possible d logs that you have in your differential equation, all the possible independent d logs. Why are they called alphabets and letters? Well, remember that when I write down the solution, I get iterated integrals, which have these sequences of omega 1, omega 2, omega 3. And the omega 1, omega 2 are just the d logs. So you have your letters, which are the d logs, out of which you form these words, which are sequences. And the set of all letters you call the alphabet. Okay, so it's a very natural language. So these omega 1, omega 2, omega 3 sequences, which sit in the iterated integrals, those are the words. D logs are the letters. Okay, so the simplest case I can have then is I have d logs, and the arguments of the d logs are linear. And, well, what comes out in that case, I think this is something that many of you know. For example, if you have something that is linear, you send just a single integral of a denominator that is linear, or d log that is linear, you get a log. Those are just the log. For example, well, you could also, maybe let's write it like this, then it would match precisely the kind of things that we had in the massless box. If you continue, because now I could write down iterated integrals where I have two differential forms. Then you get things like the dilogarithm, LE2. So that would be when you look at a sequence of iterated integrals. For example, this quantity here, if we use our notation with two words, so this would be the integral from 0 to x, d log x, d log 1 minus x. Should be the minus sign. If you want this notation of omega 1, omega 2. Omega 1 would be d log x, omega 2 would be d log 1 minus x. And you can continue like this. Now you can go on, you get classical polylogarithms if you iterate even more. So that would be d log x, d log x, d log x many times, in the very end, d log 1 minus x. And I guess many of you also know, if you continue this, then you get to something called multiple polylogarithms. This is linear forms for the denominators, but you allow for additional variables, the AIs, which tell you where the position of the pole is. So those are the kind of special functions you often get for Feynman integrals, so that is multiple polylogarithms. Now, I was a bit quick on this. If you want, we can talk a bit more. The reason I was a bit quick is that there was a whole lecture on these functions at the SAGEX school 1.5 years ago in Hamburg. So if you go to the SAGEX page, you find a link to that lecture, which as far as I remember was recorded. I'm not 100% sure, but definitely find the material there. So there was a whole SAGEX school already, well, not school, one lecture at the SAGEX school just on these functions. So that's why I don't want to spend much more time on this, because otherwise those of you who have attended the Hamburg school 18 months ago may get bored. And it's not so important to understand the rest of the lecture. Just to say that whenever you have d-logs of linear arguments, you naturally get this class of special functions, which are called polylogarithms. They are very well studied in mathematics and in physics. And that is important, because if you have a class of functions that is well studied, it means that you can factorize the problem. So imagine you would just say, well, I get these iterated integrals, I'm done, right? Those are sometimes called Chen iterated integrals. That's fine, that is the answer. You choose a path and integrate from the beginning to the endpoint, that is mathematically the answer. But it would also mean that for every problem that you want to solve, you would have to sit down again and understand the class of, understand these integrals. You would need to code up routines to evaluate them numerically. You would have to understand how to analytically continue them to all the different kinematic regions. If you know that you get a class of special functions that is well understood, that problem has probably been solved once and for all. So people have studied for these polylogarithms how to numerically evaluate them, how to analytically continue them. And so you don't have to do it again. So if you know that you can evaluate your integrals in terms of some known functions, known here means that they have been studied in the literature, then you can just rely on that. So you don't have to reinvent the wheel. In particular, for polylogarithms, there are several computer tools, in particular also Mathematica, which you can use to work with polylogarithms. So there are several mathematical implementations of, subclasses like what's called harmonic polylogarithms, but also these multiple polylogarithms. There are also maple implementations, and there's several dedicated implementations for numerical evaluations. And thanks, Lucy. I just saw that Lucy put on the chat the link to the SAGEX school in DZ. So if you look at the chat, you find a link to that school where you can find the details about polylogarithms. And that's why I'm not going to say more about these functions now. I just wanted to remind you that that's how they show up. And for the details, you can look at this, the other SAGEX school. Okay. Any questions about this? Okay, I don't see any. So then let's move on. So let's make alpha more complicated. So let's still look at the case where I have the alpha i's, the d-logs of the alpha i's. We said when the alpha i's are all linear, then that gives me polylogarithms. But now I can ask, what if my vector x here, where my x is a vector of more than one variable? Maybe still linear, but depending on many variables. What if it is not linear? Either not linear in one variable, but even possibly a polynomial in many variables. What kind of functions would I get? What if they're not even polynomial? What if I'm in the general case? And can I come up with cases where I still get to classes of known functions that I understand and for which I can use the existing Mathematica, Maple, C++ implementations? And so let's look at these three cases one by one. Let's look at the first case where we say the argument of the d-logs depend on more variables. And we're always going through an example, because the examples here are more useful than general formulas. So let's look at the case where I have just a one-fold integral of a d-log, and the d-log depends on two variables, x and y. So I have now a linear form of two variables, x and y. So, and that here you will see how useful it is to think of these things as differential forms. Because what it means geometrically is that I'm in a two-dimensional space with coordinates x and y, and I chose a path, gamma, in that space, say that goes from, let's say, the origin, 0, 0, to some point which I call here x0, y0. Maybe calling it x0, y0 was not the smartest choice, because so far I call x0 the initial point, but never mind. So I have a fixed beginning of the path at the origin and a fixed endpoint at x0, y0. And I also drew in gray the line x plus y plus 1 equals 0. That is the line where the argument of the log is 0. So that is where I would have a singularity. I would have a log of 0 or 1 over 0. Okay, so what is this integral? This is something that may come out of a differential equation. Well, here we should remind ourselves of the properties of iterated integrals. Because, well, I have this complicated curved path, but we said that I don't depend on the path. I could choose any path. As long as I don't cause any singularity, I can deform gamma in any way I like. So the idea is maybe you can choose a path such that you know that you can evaluate this thing in terms of other classes of functions, which may have already a numeric implementation. And for example, here what you can do is you can choose these two paths, gamma 2 and gamma 1, as shown here. You move along the directions where one of the coordinates is constant. Note that I can easily deform the path gamma, which is in red, to gamma 2, gamma 1, without crossing the gray line. The gray line is where the singularity is. So if my path would have to cross this line, then I cannot continuously deform it. Here, I can continuously deform it, no problem. And so let's see what it becomes if I now write down the integral. Well, I can write down the integral actually as a sum of two individual integrals over gamma 1 and gamma 2. And remember, we have seen 10 minutes ago the analog of this easy formula of just writing things as a sum of integrals over gamma, gamma 2 for general iterated integrals. I can always write down any iterated integral over gamma as a sum of iterated integrals over gamma 1 and gamma 2 individually. So we have seen the general formula before in path composition. And so let's see what happens if I look at it in this way. What does the blue and the green become? So the blue path, actually, let's look at it carefully. The blue path goes from the origin to the point x0, but y is still 0. While the green path goes from x0, 0 to the point x0, y0. So you can easily see that actually the blue path is such that y is constant and is fixed to 0, while x goes from 0 to x0. Or I can write it as x0 times t, where t goes from 0 to 1. And gamma 1 has now x0 fixed, because I'm going vertically, so the x-coordinate is fixed, and it's starting from the point x0, 0. And I have to go to the point where the y-coordinate becomes y0. Or in other words, my path segment gamma 1 is just y equals y0 times some coordinate, let's call it t prime, the prime just to distinguish it from the t that I had in gamma 2. And t prime goes between 0 and 1. So those are my two paths. So now let's see what does the integrand become on each path. So now we just do what we said before for the differential form. So now I have to write every dx and every dy in terms of the coordinate on the path. For example, for the blue one, dx is obviously x0 dt, while dy is 0, because y is 0. And so if you look at the differential form, d log 1 plus x plus y, well, first I can write it as dx plus dy over 1 plus x plus y. This is just the integral of the log. And now you plug in what you know what x, y, dx, and dy are. And you get dt over t plus 1 over x naught. But that is indeed literally what you would expect from polylog. You can do the same on the vertical path. So x equals x0. x0 is a constant, so dx is 0. d of the constant is 0. Y is y0 times t prime, so dy is y0 times dt prime. And now you can again write d log 1 plus x plus y in terms of these coordinates. And you get dt prime over t prime plus 1 plus x0 divided by y0, which is again one of these linear forms in one variable that define polylogs. And so you see that by deforming the path, you can immediately see that this is just a sum of two polylogs. I write them here as g's, but they're actually logs. Now you can say, okay, well here this is trivial, because I could have reached the same conclusion by saying this is the integral of d log, so that is clearly log. But I wanted to give you the full reasoning, including the path parameterization, because in this way, if you have complicated integrals where you have more d logs, you can go through the same argument and write the integral of the d logs, the iterated integral of the d logs instead of polylogs, by choosing these horizontal and vertical path segments where one of the two coordinates is a constant. Okay. Questions? Okay, so I don't see any questions. Let's move on. So this shows you what you can do if your alpha is linear in more than one variable. You still always get polylogs. It's not restricted to being linear in one variable. It can be linear in many variables. You always get polylogs by the same argument. So what if it's polynomial, but not necessarily linear? So let's look, for example, at an integral of 2 plus x squared. So this is actually very simple. It's actually simpler than the previous case, because you can easily convince yourself that, well, if it's a polynomial, I can just factorize it. So it's the integral of 2 plus x squared. Well, the argument is 2 plus x squared. It's quadratic in x, but a quadratic polynomial, I can factorize it always into linear factors. I may have to introduce square roots, I may have to introduce complex numbers, but I can do it. And then you're back to the previous case. So if you have something that is polynomial, but not necessarily linear, you can always go back to the case where the arguments are linear and you get polylogs. So
Carlos has a question in the
yes,
chat.
Actually, that is the next comment. No, not so. Carlos asked if it's a polynomial in one variable. No, the argument goes through even if it's a polynomial in 25 million variables. The important thing is a polynomial. If it's more than one variable, you have to combine it with what we said before. So because now I can first go to deform the path into a path where I keep all variables but one constant. But that's what we did before. And then you factorize it in one variable at a time on each line segment. So whenever you have d logs of polynomials, you can write it in terms of polylogs. Okay. So also the case where the letters are polynomial, doesn't matter how many variables, you will get polylogs. Okay. So this case is actually simpler than what the argument had before, but I wanted to do the many variables first, because then you see that the argument that we had for many variables but linear allows you to apply this to polynomials in more than one variable. So many variables, you deform the paths so that you can have all but one variable constant. Polynomials that are not linear, you factor them after you deform the contour. So then let's look at the next case. What if the alpha I are not polynomials? You can say, well, what if they are rational functions? Rational functions are not polynomials. Rational functions or polynomials are the same, because if I have d log of a rational function, it's something like this. It's a ratio of two polynomials. Clearly, that is this. So rational functions, polynomials is the same. So let's do not look at rational. Let's go straight to cases when the letters are not rational, because that is then an interesting case. That is the case when the alpha I are algebraic, in particular when they contain square roots. And here things get tricky. So here we actually have to distinguish cases now. Case one. And before we, well, it says the roots can be rationalized, but to understand what we mean by that is, let's look at the example. Let's imagine I have a letter alpha 1, which is 1 plus square root 1 minus x squared. It's clearly not a polynomial. Now, what can I do? Well, I can change variables from x to t, for example, from x to t. And I just give you here a change of variable, such that if I write alpha 1 in terms of that variable t, the square root becomes a perfect square. Well, the argument of the square root becomes a perfect square. You can easily check if you replace 1 minus x squared by this, well, x by this, you get this, which is actually not a rational function. Oh, sorry, maybe it's not very clear. This is the square root. This is what comes out of square root 1 minus x squared if you replace x by this function of t. We actually realize that the argument of the square root becomes a perfect square. It's a very easy calculation. So there are cases where you have square roots, but these square roots are, well, you could say they are fake. They're not fake, but they are just an artifact of the variables that you chose. You could choose other variables where you have no square roots. Okay. Clearly, in those cases where you can rationalize the roots, rationalizing the root means you find a change of variable such that the square root goes away. Clearly, in those cases, you go back to the cases we have already discussed, and you get polylogs. Okay, because now in the new coordinate t, the arguments of all the letters are rational functions, polynomials, and therefore, what we said before, you get polylogs. Okay, so how can I find this change of variable? That is where, of course, all the art is. Finding this change of variable, or not finding it, showing that it doesn't exist, can be extremely tough, especially if you have more than one variable. If you have only one variable, then there are strategies how to do it. which are in particular implemented in this Mathematica package, rationalized roots, by Marco Bisi, Pascal Wasser, and Stefan Weinzierl. If you have more than one variable, things are very tough. There are still some methods which are implemented in this Mathematica code, but then it gets tough. For now, the take-home message is that if you have a square root, you should check if you can rationalize it. Because if you can rationalize it, then you know how to evaluate integrals in terms of polylons. Okay. So then there's the question, what happens if you cannot rationalize it? And there are cases where you can actually prove mathematically that there's no change of variable whatsoever that would rationalize the root. So what can happen? The roots cannot be rationalized. And I give you an example here. And while the example may look a bit artificial, but the lesson you learn from the example, I think, is important. So I take, as an integrand, I take 2D logs. The integrand is 2D logs. 1D log, 2D logs. And there's, in one of these 2D logs, I have the square root of 1 plus x cubed. So it's very similar to what we had before. Before we had 1 minus x squared. Now we have 1 plus x cubed. The difference between changing x squared to x cubed inside the square root is dramatic, because you can actually, so for 1 minus x squared before, I gave you a change of variable that rationalized the root. If you change the square to a cube, you can actually prove mathematically there's no way you can find a change of variable, a rational change of variable. Okay, when I say change of variable, I always mean it's a rational function, because I want to get rid of square roots. I do not want to make it even more complicated. So it should be a rational change of variable. If you change the square to a cube, you can prove there's no rational function that rationalizes the root. It just doesn't exist. Okay, and so this is an example of something where the root cannot be rationalized. Then you have these rows and row bars, they're just third roots of unity. Why those? Well, that is because the example that we're going to construct now, I think it's the only example we know where things happen the way they're going to happen now. And so let me integrate omega over two regions, one which I call sigma 1, which is defined by this condition. Note that that gives me an iterated integral, because I require that x1 is always less than x2. That gives me an iterated integral. And sigma 1 is the iterated integral of omega, which has two pieces, omega 1, omega 2, over the line segment from -1 to infinity. That's what it means. Okay. While I also consider another region, which is sigma 2, which is the same thing, except that I don't start integration from -1, I start integration from 2. So it's very similar. But what we will see now is things, even though just changing the starting point of the integration makes the result very different. Because what's going to happen? So if I choose sigma 1 as integration region that goes from -1 to infinity, the real part of this integral, you can evaluate it analytically, and it gives you something that is -2 pi times square root of 3 times lambda of f comma 3. So you probably have never heard of lambda f comma 3. It's just a complicated name for something that in math is called a period of a cusp form. That itself is just a complicated name. The important thing is that this is something where mathematicians can prove to you that that thing, you can never, ever write it as a polynomial. Never, ever. There's no way. You can try until the end of your life, and possibly even longer, you will never manage to write this integral as a polynomial. It just does not work. Doesn't matter what this lambda f comma 3 is. The important thing is it's a known mathematical object that you know cannot be written in terms of a polynomial. So what this thing is, this is an iterated integral of d-log forms that you can never, ever write as a polynomial. Okay, so D-log forms do not evaluate to polylogs. This is a misconception that has penetrated the physics community for the last 10 years, with lots of ideas about particular n equals 4. You have D-log integrands. I mean, if you have D-log integrands, then you get polylogs and these kind of things. This is wrong. Here's the counterexample. Okay. The fact that I here only consider the real part is immaterial. Okay, is some part of the integral I cannot write in terms of a polylog. So D-log forms do not necessarily evaluate to polylogs. So what about the other guy, where instead of starting the integration from -1, I start integration from 2? And now what you get is the following. You get two terms. You get the contribution, which is actually just the original integral. Not the original, the other integral. So also this integral is not a polylog. But you get the second piece, which is a polylog. It's actually the imaginary part of a dialog. So this integral is a sum of a term that is not a polylog and the sum of a term that is a polylog. And now from that, you actually get to the conclusion that I can now form a linear combination of integration regions that gives me just polylogs. So the upshot is that the same integrand, the same D-log form, depending on the integration region I pick, gives me only polylogs, gives me something which can never be written as a polylog, or gives me the mixture of both. So the upshot is, if you have D-log forms that you cannot, with argument, you cannot rationalize, you don't know. It may be polylogs, it may not be polylogs. And the information, whether it is polylogs or not, is not contained in the integrand. It depends on the integration cycle, because depending on which integration cycle I pick, I may or may not get polylogs. Okay? I emphasize that because that is something that has led to lots of statements in the physics literature in the last 10 years that are actually wrong. Okay, so let's summarize this. So that was the case we discussed. So we started off with saying, okay, we have a canonical form where A1 is 0, and so A2 takes the form of the sum of terms, each term being a constant matrix times a d-log of some letter, alpha I. And this letter, alpha I, is an algebraic function. So it's rational and may contain square roots, for example. And what we've seen is that whenever the alpha i's are all polynomials, or all rational functions are just ratios of polynomials, then I can always evaluate it in terms of polylogs. How do I do it? Well, we saw these two things. So if it's more than one variable, I first choose a path that is a composition of segments, such that on each segment, all variables one are constant. So on each segment, I just have one variable. And if I have polynomials in one variable, I can always factorize them, and I can do the integral in terms of polynomials. Instead, if you have letters that contain square roots, then it's harder. So in some cases, you can rationalize all the roots, and there's this Mathematica package, rationalize roots, that you can use for that. And then you go back to the previous case. Then everything is back to polynomials and rational functions, and you're back to the previous case. But if you cannot, it depends. Just having D-log forms does not mean you get polynomials. Okay? Questions about that? Okay. I don't see any questions. Good. Then for the last 10, 15 minutes, let's spend some words on what happens in the case when A1 is not 0. So we said that here I could find a transformation M rotation that is made out of algebraic functions, rational functions, square roots, such that I get to a canonical form, meaning A1 is 0 and the matrix is proportional to epsilon. So what if I cannot achieve A1 equals 0 by some rotation that is an algebraic function? So the upshot is that if A1 is not 0, then definitely will not get polynomials. We'll see why in a minute. Well, actually, no, it's clear that you cannot. Why can you not do it? Because if you could write the answer in terms of polylogs, well, polylogs have the property that they satisfy a differential equation where A1 would be 0. So it's like by contradiction, right? So if you can write the answer in terms of polylogs, then there is the differential equation would be in canonical form, A1 equals 0. So if you cannot achieve that, it cannot be polylogs. Okay. Note that here I'm saying I cannot achieve A1 equals 0 with an algebraic transformation. I mean that it cannot be done. It does not mean that you have not managed to do it, okay? There's always a difference between I have not managed to do it or it cannot be done, right? It may be that you need to change a variable that is super complicated that you may not have figured out, that if you had figured it out, you could have done it. That is not what I'm talking about. Here I'm talking about a case where it cannot be done intrinsically. Showing that it cannot be done is a different story. So in that case, you can still reach some, call it a generalized canonical form. So how does that work? Well, let's first consider the following equation. So A1 was not 0, so let's consider the equation dH equals A1H, where H is my unknown. So that is the differential equation, first order, linear. A1 is matrix. Say if A1 is an n times n matrix, or H is a vector, well, the unknown is a vector with n components, there are n independent solutions. So there's a basis of solutions H1 to Hn, and I combine them into this matrix that I call H. So I construct, I have n independent solutions to the system, and I combine them into a matrix. Note that this matrix is nothing but the matrix that you would have gotten from path order exponential. Okay. So if A1 is not 0, I can look at this equation, which just has A1. So this is like putting epsilon equal to 0. So what can I do now? Well, my system that I want to solve is the one that has A1 not equal to 0. So it has epsilon not equal to 0. So it has this term in addition. And so now let me change bases from J to K with this matrix H that I found. So if I do that, well, I can work out what happens. So I compute the differential of J. I get two terms, dH acting on K and H acting on dK. But dH is A1 times H. And so if you compare it to what we had in the very first line, you actually see that the A1 term goes away now, and that what is left is a new system which is in canonical form. Epsilon is factorized, where this new matrix B is now given by this. It is H, the inverse of H times A2 times H. So I have reached the canonical form still. But there's a crucial difference. Namely, the H that I've obtained cannot be algebraic, meaning it cannot be D-logs with arguments that are rational functions or square roots. It cannot. Why can it not? Well, if it was. So I started from the assumption that I cannot find any algebraic transformation that brings me to canonical form. So if my B was algebraic, an algebraic would imply, this would imply that B has this form. Well, algebraic would mean that, well, this form would be algebraic. If B was algebraic, then my original assumption that I cannot get rid of a 1 with an algebraic transformation would be wrong. So if I cannot get rid of A1 with an algebraic transformation, I cannot reach a canonical form with D logs only. I can still reach a canonical form in the sense that epsilon is factorized, assuming I can solve the equation that I have here at the bottom. If I manage to solve that equation, if I find all the solutions, all the n solutions of that equation, and I combine them into that matrix H, I can bring my original differential equation, which is here, to the canonical form, which is here, with this matrix. But this matrix B cannot be a matrix of D logs of algebraic functions. Now, what will happen is that this matrix B will involve then other objects. It would not just be D logs. But instead, what it will involve is things like, so someone posed a question in the chat, do we know examples of these non-algebraic H? Yes, that is what I'm just about to say now. For example, the matrix B would, for example, involve things called modular forms. So it would involve periods of Calabi-Yau varieties. In general, the H would be the periods of some algebraic variety. For example, the periods of an elliptic curve, or the periods of some K3 surface, or the periods of some Calabi-Yau varieties. And they will then propagate into B, which would make B into things like they would not be D logs, a matrix of D logs, it would be a matrix of modular forms, for example. This is what happens for things like the massive sunrise. So you would get different classes of iterated integrals, which would definitely not be expressed in terms of polylogs. You see it again here because polylogs are iterated integrals of D logs, and I said that my matrix B is definitely not a matrix of D logs. So again, you see that it cannot be polylogs. It is something else. Now, this is getting then quickly very complicated. And you're running out of steam even with the mathematics. So iterated integrals of modular forms are still well understood, well, reasonably well understood. As soon as you go to more complicated geometric objects like K3 surfaces of Calabi-Yau surfaces, it's getting super complicated, and even mathematically not much is understood. I should, however, mention that there are numerical methods to solve these differential equations, in particular to solve differential equations of of this type here. You can solve this numerically. In which case, of course, you don't care what kind of functions. Okay. Good. I think that's more or less all I wanted to say. So since we started late, we still have a couple of minutes. So if you have questions, feel free to ask questions, so either about the lectures or about the projects. And otherwise, thank you very much for your attention.
Let's unmute ourselves and give Claude a round of applause for all 3 lectures.